Imagine a secret code embedded deep within the heart of atoms that determines their stability, a set of special numbers, so influential they dictate whether an atom can endure for billions of years or decay in mere moments. These are known as the magic numbers in nuclear physics, and understanding them unlocks profound insights into why some elements are incredibly stable, while others are fleeting. Take lead-208, for example. This isotope boasts a nucleus that's one of the most enduring structures in nature, likely to persist indefinitely. On the other hand, technetium-99, a man-made isotope, vanishes within a few hours. What accounts for this dramatic difference? It all boils down to the atomic nucleus's architecture, specifically the unique counts of protons and neutrons it contains. When these nucleons fall into the so-called magic numbers, the nucleus becomes remarkably resistant to radioactive decay. But what exactly are these magic numbers, and what makes them so special? At first glance, one might think stability is simply linked to an element's weight. Heavier atoms tend to be less stable and more prone to decay. Yet in the 1940s and 1950s, researchers spotted something curious. Many lighter elements also featured radioactive isotopes, such as carbon-14 and potassium-40. These isotopes decay slowly, contributing a steady background radiation to our planet. The mystery deepened when scientists noticed that nuclei with certain exact numbers of protons and neutrons exhibited surprisingly enduring stability. These special values earned the nickname magic numbers. David Jenkins, a nuclear physicist at the University of York in the UK, offers some clarity. The magic numbers are 2, 8, 20, 28, 50, 82, and 126. If you look at the smallest case, 2 protons and 2 neutrons, you'll recognize it as the nucleus of a helium atom, which is known for its remarkable stability. Here's where it gets fascinating. Helium nuclei, also called alpha particles, are often emitted by larger, unstable atoms during radioactive decay. This emission might seem puzzling at first. Why would an atom shed a chunk composed precisely of 2 protons and 2 neutrons, rather than losing nucleons one by one? Jenkins explains that the alpha particles' own exceptional stability, the result of these magic numbers, makes it energetically favorable for the atom to emit this specific cluster during decay. Other well-known magic nuclei include oxygen-16, with 8 protons and 8 neutrons, calcium-40, 20 protons and 20 neutrons, and lead-208, 82 protons and 126 neutrons, the heaviest stable element humanity has discovered so far. Trying to understand these phenomena led physicists to propose the nuclear shell model, a concept somewhat echoing the arrangement of electrons in atoms. The idea is that protons and neutrons reside in distinct shells, akin to electrons orbiting the nucleus, Jenkins details. When energy is absorbed or released, nucleons jump between these shells. Much like electrons, these nuclear shells exist at specific energy levels, known as quantized states. Stability peaks when these shells are completely filled, creating a configuration that's energetically favored. The explanation behind this phenomenon is rooted in quantum mechanics, a branch of physics that explains the behavior of particles smaller than atoms. A key player here is the strong nuclear force, the fundamental interaction that binds protons and neutrons together. It turns out this force is surprisingly stronger when nucleons occupy a full shell, enhancing the nucleus's overall stability. So, magic numbers essentially count how many protons or neutrons fill these shells exactly. Some isotopes are singly magic, meaning they have either the magic number of protons or neutrons. Iron-56 is an example. Others are doubly magic, containing magic numbers of both protons and neutrons. Oxygen-16 and lead-208 fit into this rare and special group. Doubly magic nuclei are scarce but intriguing. Jenkins points out an elegant detail. These doubly magic nuclei shape themselves into perfectly spherical distributions of matter and electric charge, an unusual trait since most nuclei are distorted and rotate rather than form perfect spheres. This spherical shape is more than a curiosity. It reflects their uniquely stable internal structure. But here's a thought-provoking twist. The limits of this nuclear shell model are still unknown. Take Tin 100. For instance, a doubly magic nucleus with 50 protons and 50 neutrons. It's fascinating, yet its half-life is a fleeting 1.2 seconds. Then there's unbihexium, a predicted magic element beyond lead, which scientists have yet to create. This uncertain frontier raises a tantalizing question. Could these magic numbers pave the way for expanding the periodic table into as yet unseen territories? Or do their stabilizing powers have natural boundaries? And this is the part most people miss. While magic numbers provide a powerful framework for understanding nuclear stability, they also highlight unanswered questions and fuel ongoing debates among physicists. What do you think? Could the concept of magic numbers be the key to unlocking new elements and expanding our understanding of matter? Or is it time to rethink these assumptions? Share your thoughts and join the conversation.